As shown in this slide, consider two tasks in the dishwasher system, the higher priority water manager and the lower priority display manager. There are two figures shown on this slide. The upper figure shows visual of the two tasks in form of their function, while the lower figure shows time continuum of tasks executing on the microcontroller embedded in the dishwasher. At time t1, water tap is on and the dishwasher chamber is being filled with water. Exactly at this time, the display manager is updating the display and has printed GOO on the display, which is part of the complete message good status that it wants to show on the display. Next, at time t2, the dishwasher chamber is full so that there is a need to shut off the water tap. At time t3, immediately after time t2, the display manager is paused, that is preempted, and the water manager swings into action and shuts off the water tap. Notice that the display at time t3 is still showing GOO. Only after the water is shut off at time t4 that the display manager is able to complete its work and the display is showing good status. Notice on lower figure that the display manager is preempted by the water manager between time t2 and time t4. But which authority in the system decides which task runs at what time? Well, that's the job of the scheduler. A scheduler in the system lines up tasks in accordance with their priority. It works as an arbitrator. At any given time, it decides which task must perform its job and which task should be paused. Thus, when water needs to be shut off in a dishwasher, the scheduler decides that the lower priority task, the display manager, must give way to the higher priority task, the water manager. Only after the water manager finishes its job that the scheduler allows the display manager to continue its work. Thus, in effect, the scheduler in real-time system maintains a ranked list according to the priorities of all the tasks in the system. And by means of preemption, the scheduler enforces the ranked list by allowing or disallowing any particular task to perform its job at any given time. Hence, the typical scheme employed for scheduler in real-time system is called priority-based preemptive scheduling. Quite mouthful, huh? That brings us to the end of this seminar. Let's summarize the concepts we have just covered. A basic unit of operation in a system is a task. A system may have multiple tasks running at any given time. Tasks in real-time systems have deadlines. If tasks fail to meet deadlines, dire consequences may follow. According to their importance, tasks get assigned priorities. The higher the priority, the higher the importance. Higher priority tasks can do their job while pausing the lower priority tasks. This is called preemption. Scheduling scheme enforces priority-based preemption to maintain coherency of the system. Lastly, if this seminar has incited enough interest, please do read more on the topic at the references shown on this slide. The easiest to find and have fun with is the Wikipedia at www.wikipedia.com. On this website, search for the word RTOS, and cruise on from there on. Another very helpful resource on real-time system and operating system concepts is a book written by Jean Labrosse, who is also the author of Microchips. This real-time operating system is ported on all Microchip microcontrollers. His book has abundant reading material for novice as well as experienced programmer. And finally, my all-time favorite book on introductory concepts of operating systems is written by Andrew Tannenbaum. It covers aspects of general purpose as well as real-time operating system software. With that, I shall say goodbye, and please don't forget to provide your feedback on this seminar. Thanks for your time today.